Yes. Tonight we're just going to have a brief discussion on thermometers and temperature scales. So, we have heard of these words before. Thermometer. Yeah, we have heard of this word thermometer, and we have heard of the word temperature. But there's an interesting other term which they have added, which is scale. All right. So they have added another interesting concept which is called scale. So scale is a means of measurement, comparing one thing to another. So when you have a scale, then you have a means of measurement that can compare one thing to another, so that you can have a numerical representation of the results, the data that you get. So we usually use scales. Now, before we go any further, let me ask if there's anyone who can define for us what temperature is. What is temperature? Temperature. Because they may ask a question in physics to say what is temperature. So let's see if you guys can help me and help us understand temperature. What is temperature? Anyone? Anyone?
Temperature is how hot or cold something is, an object is.
Okay, how hot or cold an object is. Awesome. So anyone else again? Anyone else to give us another definition, or are we satisfied?
Yeah, I'm satisfied with that.
So, I'm sure you guys have also done a bit of temperature-related concepts in chemistry. I don't know if you have done so, but in my chemistry one time I came across the definition of temperature, which says temperature is the average kinetic energy of a body, the average kinetic energy. So of course we are used to knowing that kinetic energy is unless an object is moving, like with a velocity. But actually, you'll find that the velocity of an object, for example, at an atomic scale, all right, molecules and atoms, you find that if you freeze a substance, if you get a container containing substance, containing matter, whether it's a solid, liquid, or anything, if you get that container at room temperature and you get a microscope, what you will observe is you observe atoms moving. Have you ever wondered why you put mazoe at the bottom of a juice, at the bottom of a cup, then you pour in water without even you getting a spoon to stir it up? You find that the whole cup is tasting sweet because of the mazoe. Have you ever wondered why it is like that? You put mazoe at the bottom, but then when you add water without even stirring, you find that the whole cup is sweet. Have you ever wondered why?
No.
Okay, you should be wondering why this mazoe is tasting sweet. It's good science to always wonder why things happen. But actually, why it happens so is because the mazoe that you had put in is moving. It's not going to stay at the bottom. It will want to move around the whole fluid and interact with the rest of the liquid, with the rest of the water. So due to the movement of the molecules of mazoe and water moving in that cup, you get the whole cup to be sweet because of movement. I'm sure you will learn something like that in chemistry. So but that movement can be stopped. How can we stop that movement? Is if we freeze the water. Imagine you get what's this? Mazoi, you freeze it. You get also water, you freeze it. Then you mix them. Do you think you taste any sweetness in the water? It won't mix, like things won't move, right?
Yes,
Because
sir.
yes, because it is frozen. So if you remove temperature, if you remove heat, if you remove heat, which is measured in terms of temperature, not the heat energy, but just heat, which is measured in terms of temperature. If you remove that heat, you discover that the molecules won't move. So the movement actually can be very much related to temperature. All right. So that's why we say that temperature is the average kinetic energy of the body. But here in physics, they have defined it as the measure of an object. In fact, here they missed a word. It is the measure of an object readiness to spontaneously. So it is how ready it is to spontaneously give up heat energy. All right. How ready. So of course here they missed a word. If I don't know if I can write it. Okay. So they missed a word, maybe readiness there. Readiness. Okay. Anyway, we know what I want to write. So it is the measure of an object readiness to spontaneously give up heat energy. All right. And so we are going to explore more about this concept of temperature so that we get to just appreciate more tonight on this, how we can use thermometers to measure temperature. In fact, a thermometer is an instrument that is used to measure temperature. So let's go down and just look at some of the ways that we can appreciate this concept of temperature. So I'm sure you guys are familiar with the temperature scale of 0 to 100 degrees. Are you familiar with the temperature scale of 100 degrees? 100, or should I say from 0 to 100 degrees Celsius. Are you familiar with this scale?
Yes.
So now, one thing that you have to realize is that for temperature that we normally use, or how we normally measure temperature in our everyday life, is we get a convenient way of measuring temperature by just saying, okay, we'll be measuring temperature from 0 to 100 degrees. 0 to mean, how many know what 0 means? What special things happen at 0 degrees? At 0 degrees Celsius, what special thing happen?
Water
This
freezes.
is freezing.
Okay. Awesome. We know that at 0 degrees, that's where water freezes, and water is the most abundant fluid. So it is very good for us to make a reference of to say, okay, 0 degrees is where water freezes. And someone to help us with what happens at 100 degrees Celsius. What happens? What special thing?
That's what the boiling point is.
Awesome. Awesome. So again, as you will see in the later texts, as you will discover more, you will discover that this idea of saying just 0 degrees, 100 degrees is not sufficient for us to even describe what happens to water. You see, for example, if we just say at 0 degrees is where water freezes, actually that is not correct. We should also add another term. We should say at 0 degrees Celsius under atmospheric pressure, ATM, atmospheric pressure. So the pressure has to be that of atmosphere, 1 atmosphere. So if we have 1 atmosphere, we expect that water will freeze at 0 degrees. If we change the pressure, as you will see here in the later texts, you discover that if you change the pressure, even the freezing point will change. If you increase the pressure, you discover that the freezing point will go low. It will be lower than 0 degrees. But if you reduce the pressure, you discover that the freezing point will go. In fact, no, I said it the other way around. If we increase the pressure, you find that even anyway, for now, let us not consider much about pressure because we will talk about it later on in the later texts. But for now, we're just trying to understand temperature. And the one who came up with this scale of from 0 degrees to 100 degrees is a man known as Celsius. All right. I'm sure you have heard of the word Celsius, degree Celsius. Sometimes we even use degrees centigrade. So there's a man known as Celsius. Let me just get rid of this. There's a man known as Celsius. This Celsius man is the one who gave us the scale of from 0 degrees to 100 degrees to mean from the point where water freezes to the point where water gets to boil. Now, what you see here on the diagram here is just a thermometer that uses mercury or ethanol. Actually, this one uses ethanol, which is like alcohol. And so you discover that a piece of instrument like a thermometer, which uses alcohol, will be based upon the effects of temperature on this liquid. So if we put a liquid in this tube there, we'll discover that if we increase the temperature, the liquid will start expanding, and then we can be able to measure the expansion of the liquid and make it relate to the temperature. But we'll talk more about the expansion and pressure and volume relating it to temperature when we come to another section. But tonight, I just wanted us to establish just the basic ideas of temperature. Just to know that temperature, like Precious said, is the measure of how cold or how hot an object is. But you may not use that definition for now, since you guys are now university students. University students now just don't look at the measure of how cold and how hot, because there's more to the coldness and there's more to the hotness of a body other than just what you feel. When you touch an ice block and feel cold, there's more to that ice block, all right? And there's more to water which is boiling when you touch it and feel warm. So tonight is just we're just appreciating the idea of temperature as we start this topic, and hopefully we'll be able to manage to prepare more or have more or cater much concepts which would make us ready for the quiz on Friday. All right. So Let me just talk a little bit about Celsius. So, like I said, Celsius gave us a scale of from 0 to 100 degrees. But there's also another person by the name of Kelvin. Now, Kelvin gave us another scale where Celsius actually derived from. All right. So, with our friend by the name of Kelvin, his temperature starts from 0 Kelvin and it goes on to infinity, hot Kelvin. All right. So now from 0 to infinity, there are a lot of numbers here, and sometimes using them in normal everyday life can be cumbersome. So now Kelvin realized that what we observe in normal daily life is that at 273 Kelvin, when we measure temperature at 273 Kelvin, what happens? What is a special thing that happens at 273 Kelvin? Anyone to help us?
Freezing point.
Awesome. So Celsius realized that at 273 Kelvin, that is where water freezes. So we have water freezing. And then when he went further and checked, he discovered that at 373, what happens at 373 Kelvin? Let's go. What happens at 373 Kelvin?
Water
Boiling
boils.
point.
Awesome. So he discovered that from 273 to 373, here we have boiling, but here we have freezing. Then he discovered that the scale from 273 to 373 was divided into 100 units. 100 units. All right. From 273 to 373, we have 100 units. All right. So now these 100 units is what now Kelvin said, for convenience sake, we must look at this scale from 0 to 100 for measuring temperature in our normal daily life. Because when we are measuring body temperature and whatnot, usually things don't go beyond 100 units, 100 degrees Celsius. But of course, sometimes we even measure temperature 200 degrees, 300 degrees, and it's easier to work with those numbers other than to work with 273 Kelvin, 373 Kelvin. So this is how our friend Celsius helped us to make life easy. All right. Now, with that said, whenever you are given temperature, for example, if they give you 200 degrees Celsius, all right, 200 degrees Celsius, what do? You always need to change this to Kelvin. All right. You always need to change this value in Kelvin whenever you are doing your calculations. So as we'll see later on in the texts, we'll discover that whenever you are given temperature, for example, the temperature of water is 200 Celsius and whatnot, when you are doing your calculations, make sure you change this temperature into Kelvin. And how do you change this temperature into Kelvin? And Kelvin, we have a temperature which is given by capital letter T. So our capital letter T is just, you get this 200, all right, add plus 273, all right, 273, what we have here. So when we have our temperature in Kelvin, when we are given temperature in degrees Celsius, to get our temperature in Kelvin, we add the temperature that we are given in degrees Celsius by 273, and this will give us something like 473, and this is our value in Kelvin, and then we can be able to use this value in our calculation. So be able to look out for this phenomenon, for this way of doing things, and we shall see more as we go in the text. So today is just a way of introducing what we are doing tonight, so that as we go, we have something to work with. So now let us also consider another aspect of what the Americans use. Have you ever heard of the Fahrenheit, degrees Fahrenheit? Have you ever heard of the word Fahrenheit?
Yeah. No, me have never heard of it.
Yes.
So this is the word Fahrenheit, which you see here. So now, let me just draw your attention to this diagram that you see on top here. So now this diagram that you see on top, from what we have as the temperature, especially when we are considering water. All right, when we are considering water, we know we are always supposed to be using the Kelvin value. All right, because that is the scientific standard unit for temperature. Temperature is measured in Kelvin. All right, temperature is measured in Kelvin. But the scale of degrees Celsius just helps us, for convenience sake, to look at the freezing point of water and the boiling point of water. All right, we have already established that. But there's another friend of ours by the name of Fahrenheit, and this friend said that he's an American, and then he said that instead of us starting from 0, we will start from 32. We'll start from 32 degrees. Now, it's not degrees Celsius, it is degrees Fahrenheit. So the Fahrenheit scale tells us that at freezing point, we have 32 degrees. But when water is boiling, we have 212. So what is the scale? From 32 to 212, we discover that we have 180 units. All right. So our friend Fahrenheit said from the freezing point to the boiling point, we should have 180 units. But our friend Celsius said from 0 degrees to 100, we should have 100 units. So these are the two different modes of measuring temperature that are used in the world, famously used in the world, but you discover that all of them relate to the Kelvin scale, because Kelvin is the one that is agreed upon by all scientists, and in fact is the one who gave us a scale to say this is how we should be measuring temperature. All right. Now, have you seen what I was telling you? That at 273, we have the freezing point of water. At 373, we have the boiling point of water. Now, even Kelvin also goes all the way to 0. When we talk about 0 Kelvin, all right, so 0 Kelvin is what we mean by absolute 0. So when we talk about 0 Kelvin, meaning it's very, very cold, there's no minus Kelvin. It only starts from 0. There's no minus Kelvin. But for Fahrenheit, we see that we have a minus. In fact, at this 0 degrees Kelvin, in Fahrenheit, we have minus 459.69, because it has even gone to the negatives. At this same 0 degrees Kelvin, we have a temperature in degrees Celsius as 273. Of course, they have written it 0.15, but anyway, it's usually known as negative 273 degrees Celsius. This is very, very cold at that temperature. Of course, you have heard of maybe negative 10 degrees in some countries. It reaches negative 10 degrees Celsius. But when it reached negative 273.15 degrees Celsius, then we expect that place to be very cold, such that nothing can move. If you are to find yourself at this temperature, all your molecules, all your atoms, all your everything will stop moving because it will have no kinetic energy. All right. Remember, we say that temperature is the average kinetic energy of a body. But again, we can use so many different equation definitions. But the one that scientists mostly use is the average kinetic energy, or the readiness to spontaneously give off heat. All right, as we saw in our preamble. So for tonight, we just wanted to introduce the concept of temperature because we'll be using it mostly in our lesson in this chapter. So I guess if we don't have any more questions, in fact, before we end, I just want to show you how we can convert from degrees Celsius to Fahrenheit. All right, let me just rub what I wrote here so that I can show you the slide below. So here is something special for you to look at. All right. So for example, if you have been given your value in Fahrenheit, if you are watching news and you hear that in America it has reached 100 Fahrenheit, all right, then you are wondering how hot is it really? You can easily change it into Celsius by doing Fahrenheit minus 32 over 9 is equals to Celsius over 5. All right, so you can change from Fahrenheit to Celsius like that. All right, the more way of maybe looking at it is also this expression. 50 degrees Celsius is equals to 122 degrees Fahrenheit. All right. So I guess this is just for us to appreciate the concept of temperature. If we don't have any more question, then we can end here. Do we have any more question?
Sir,
Mm-hmm.
since you're saying that the same formula, which is saying F minus H2 over 9 is equal to C over 5,